Now for step 3 is where we have to do some pretty heavy lifting, and we need to find our chi-square statistic. So let me remind you what that looks like. Hold on one second. There it is. It's chi0 squared is equal to the sum of the observed minus the expected over the expected. Oh, squaring, and then over the expected. Matter of fact, I'm just going to put that kind of over here for our own little benefit so we can see it. So that means we're going to need to take the time to actually find observed minus the expected, square them, and then divide them by the expected. All right. So we observed this, parentheses, B6, or B2, excuse me, minus C2, that's the expected, close parentheses, square it, and then divide it by that expected value. And then you can just move your clicker over here to the plus and double click, right? So it's part of the handle. And it said in the assumptions that they don't want any of them to be lower than 1, which we don't have. They're all greater than 1. And no more than 20% of the expected counts are less than 5, which we only have 1 out of 5 that's less than 5, so that's good, right? So 20%. Okay, so now the statistic. Let me write it down over here. Test statistic, the chi-square test statistic. Say that 5 times fast. Statistic. Okay, it's going to be equal to, you know what, I might as well find the sum here. Equals sum of that value. There you go, 121.367. So we wanted to add all those up, so that's the test statistic right there. So if you just sum that column, you've got it. So that's chi0 squared. Whoops, whoa, come back. There we go. All right, now step 4. Well, step 4, as we all know, is a little bit complicated because you have 2 options. You have the classical method and the p-value method. So let's start with the classical method. To do the classical method, we're going to need the critical value. Now, the good news is that these are always right-tailed no matter what because of the way the chi-square goodness of fit test works. So you're going to want to be equal to chi.sq dot inv.rt, and then our alpha. Oh, and I need degrees of freedom, which I never found. I'll find it right here. Oops, I know it says I don't have a number, but that's because I'm about to get it. N is our count, if you will. It's really K, but whatever. It's equal to the count that are in here, right? It's the number of categories you have, if you will. So the book, I think, calls it K, whichever. Doesn't really matter. So when you have that filled in, then it knows that it's n minus 1, or k minus 1, excuse me. So it knows that it'd be 4 in our case for the degrees of freedom. Now, if you have old Excel, it'd be equal to chi inv, chi inverse, it's 2 i's in there. Probability is 0.05, comma, again, 5, take away 1, 4. All right. Oops, there's a mistake. It's over here. I forgot to tell it minus 1 for the degrees of freedom. That would be a problem. All right, there we go. There's our critical value. Okay, so now we have our test statistic and we have our critical value. And notice how much larger our test statistic is than our critical value, right? So we are going to be rejecting. So let's write that up right this second. And I'm going to put it over here because I'm going to do 2 step 4s. So I'm going to do this step 5 over here, which is we reject H0, the null hypothesis, because the test statistic, which is equal to chi-square, honestly, chi0 square, I don't want to try to type it up, so is equal to 121.367 is greater than our critical value, which was equal to 9.488. There we go. That's why to do it the classical method. All right, now next video I'm going to come back and I'm going to show you how to do it in the p-value method, and we'll do both Excel and we'll show StatCrunch as well. All right, so I'll see you then.